In this video, I'm going to talk about cache as RAM. Cache, what is cache? Cache is the memory that's inside the system on a chip, SoC, that is rapid access memory. The cache normally is used just to bring in code to execute quickly. You cannot access the cache directly by memory addresses. But in this video, we're going to show how that cache can be used as RAM directly to address without using any external RAM. We can run some code and not use external RAM. So that's where we're going next. I was a little bit wordy, a little bit different way of explaining it, but let's dive into the code. Part one, here's where we ended up. Jump boot block pre-C entry. And so I go quickly to this file called caches RAM, which is the subject of this one. And we see something very strange here. Here's the boot block pre-C entry, but this thing right here, gcccar.inc, is a macro. It's not a subroutine, it's a macro, meaning there's a whole bunch of vendor assembly code that's going to actually do most of the work for us in this thing. So AMD has graciously given the source code out for this, probably so that they should be able to make some money on it some way. But anyway, this doesn't hurt their profits to give out this source code, because then they tend to get used in open source uh, BIOS like we're talking about here. So with that getting too busy talking about that, let's get rid of that little thing there. We'll kind of do this rough and ready. We're going to go quickly to this thing in a minute, this macro description. And notice here we are on this. Let's just get down into the business here. We don't need to read the comments here. Postcode, boot block, pre-C entry, and then what happens next? This thing right here, AMD enable stack, that's all covered in this other file called gcccar.inc, which is Grand Global Compiler, caches RAM. And anyway, let's just look at the file rather than trying to read the thing. Okay, here we go. Here's the macro called AMD enable stack, and its purpose is, surprisingly enough, set up a stack. Once we leave here, once we complete this macro, the stack will be set up, the stack segment and the stack pointer will be set up. And let's see what happens. The stack size in bytes will be in the ECX register. And there's this kind of industry specific Giza status. I can't remember what those letters stand for, but I'm trying not to get too detailed on this because we'll really get lost. Anyway, here's the thing that I found kind of interesting is that if you look at these numbers down here, the numbers start at 0 and they go all the way up to hexadecimal 1 and 5 zeros following in that. And what that means is we have, is that 5 zeros? Let's see, 1, 2, 3, 4, 5. Yeah, it's 5 zeros, which means that's 16 megabytes of, we can actually call it DRAM because that's the way that this dynamic RAM that's used mostly in computers now, the large amount. But here's 16 megabytes. That's not external, but it's contained within this system on a chip, this AMD processor chip that contains a whole bunch of stuff, including this 16 megabyte cache. So somehow we've got to convince this cache that it's going to be just regular DRAM so that we can use the stack in there. And actually, there's going to be space in here where we can actually load programs. So, believe it or not, this ROM stage of this core boot thing that we're going through is actually going to be loaded directly into this DRAM. So, let me keep moving on here so we don't get too lost, especially me get lost. Okay. Some of these comments will probably be best than trying to fight through all the detailed information here. The default stack will be this ESP, which is the stack pointer. And let's move down here. Now, a stack pointer points to the top of the stack. And we'll talk about something in a little bit called the base pointer, which will point to the bottom of the stack. Now, the bottom of the stack is going to be at higher memory addresses. The top of the stack is going to be at lower memory addresses. As we take things off the stack, in other words, reduce the amount of data in the stack pointer will increment. When we put stuff on the stack will decrement. So as you think of it, that stack's going to increment. The stack pointers, as you add things to the stack and start filling up the stack pointer will get lower and lower memory addresses. So I think what this sets up here is we'll read more about what the size of the stack is, but I think the stack is going to be somewhere around 64K big. So that's a pretty big stack. That's 64K, not for code, but just for stack bytes. And that's going to be our memory way of doing things. Okay, let's get down here. Let's see here's the details. Start loading up registers and do these machine specific registers. We reading those and writing them and blah, 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 blah. The main thing is, look at this heading on this address here. Set up stack. That's what we want to do, is set up the stack. Oh, let's see what goes on here. We move stuff around. I spent some more time going through the details of this, but let me just try to keep the basic thing set up here, is that we want to disable. Here's some other little procedures that occur. But what I want to do is look at where we set up the base pointer, which is the bottom of the stack. Various things happen. We're loading registers, mainly these machine-specific registers, writing them and reading them. And let's see, this video is getting a little bit off track here. I set this up and thought I was getting ready here, but here we go. The outcome of this block is that the EBP, that's where I was trying to get to, the base pointer, is going to be the start address of the stack block. And if we follow this code through the assembly stuff, eventually we're going to find where we load the BP. Okay, the BP is loaded with, if you look up this stack base register in the includes, you'll find out that this is address 3, hex address 3 followed by 000, which means that that's 3 times 64K. And it means that our base stack is set at 3000, which which means that we're going to have a base pointer at the bottom of that address. The stack can grow to 20000, and that's where our stack will exist. Maybe it's not so much the point of this video to step through all the intricacies of the AMD cache system, but it's just to point out what the stack is. So eventually there's some place in here where it's going to disable the stack. I think that occurred earlier. Did we disable the stack earlier? Somewhere along here there's an instruction where we disable the cache, not disable the stack, but disable the cache memory so that it acts like just 16 megabytes of DRAM. And maybe it's enough to say that this process is going to set things up so that the stack pointer, what was the key idea I wanted to point up here, is the start address of the stack block. This is kind of a review for all the details. And let's see what our goal is here. Determine the mode for the stack, the mode for the stacked segment base. And we jump, if carry, to protected mode. If you remember, we put ourselves into protected mode, so we don't want to go on, we want to jump down to that address called protected mode. And we're going to set the stack pointer. Base pointer is already set at 3, followed by 4 zeros, hex address. And we're going to set the stack base in this, that's review. So we've already set the stack base. The stack pointer should be set to initially the base pointer. So if the stack pointer, the top of the stack, equals the base pointer, which is the bottom of the stack, then that means that the stack is empty. And as the stack grows, the stack pointer will decrease memory addresses. And then we do a nice thing is we look at the 64K of stack from 3000 to 2000, and we just make those all zeros. So we don't have any stuff in there that messes with data that we don't want. Now here's a nice little thing that they put on here. They put a kind of a dummy value here. Put marker in top stack double word. So they just put these hexadecimal things that show as letters A, B, C, D, D, C, B, A, just so the that can be recognized as a well, that's what the stack pointer is. Wait a minute. Oh no, that's where the stack pointer points. That these parentheses around here are where the stack pointer points. So that's just wherever the stack pointer is, it puts this value on there. And let's see. Well, that's the end of the macro. So we should be able to go back to caches RAM. All that stuff that I just talked about were the details. That's probably, well, not, that's absolutely why we need vendor code, because that's way too complicated to put in a spec sheet and expect somebody to be able to do that without that vendor code. So all we did is enable the stack. Let's see what other steps we take here. Align the stack and keep a line for call to boot block C entry. So we're getting out of assembly code and going to C code. Let's see what that alignment does. Well, let's see what that does. If we AND this value to the stack pointer and we AND 1, you get the same thing back. If you AND a 0, you zero it out. So that means that there's going to be the last 4 bits, or the lowest 4 bits of the stack pointer is 0. So it kind of aligns it on a 16-bit boundary. Then we subtract 8 from the stack pointer, which is going to put us at, let's see, whatever the stack pointer was. It'll just subtract 8 from that aligned value. And then let's see, what else do we need to do? Oh, yeah, here's a little thing we need to do is we want to copy the data section content to cache's RAM. So we want to take the data that we have now and put that into this cache's RAM memory. So let's see how that works. Let's see where my copy data section.inc. There it is. So look what we're doing. We're pushing the register values onto the stack. So those that we're putting those, this is the first application of putting things into our newly set up 16 megabytes of RAM. And so this is loading the stack. So we're putting some stuff on there. And since we're in a 64-bit processor, we use these. This is for 32-bit. Let's see, what else we got here? Anything interesting? Not too very interesting. Then we put stuff on the stack. Now notice we do RCX, RDI, RSI. We do some stuff with those registers. And what are we trying to do? Okay, we changed the registers. The ECX register. What was that all about? Let's see. But somehow, what I wanted to point out is we pushed the RCX, RDI, RSI, and we pop them, meaning we take stuff off the stack in the reverse order. The last thing that we put on was RSI, so that's the first thing we take off. So I'm not sure what we accomplished with all that, but let's just read the code here. This code can be included from 32 bits or 64-bit codes. It also preserves registers. Okay, well, all that push and pop stuff that I thought was so great, all we're really doing is just saving the contents of the registers while we perform this operation down here. Back to cache's RAM. Let's see, postcode bootlock pre-C done. And then what we do now is our first call instruction. We've never done a call instruction yet because we didn't have a stack set up. Now that we have a stack set up, we can save the return value on the stack so we can come back. But notice what this comment says, never reached. Meaning we go to this bootlock C entry, we're never going to come back to this cache's RAM file. So this is the end of this segment so that we can get going on C code. That didn't turn out so well, but I'm going to keep it anyway because I know that the details are there if we want to dive into it. I guess what I'm trying to do is I don't want to clutter up this video with the specific details of all that stuff. It's probably just to say that it takes vendor code to disable the cache, and set up the stack.